Okay, so this is week 8. And today I'm going to talk about some inequalities for probability work, right? So let's recap some results that we learned last week. So last week we talked about Markov's inequality. So Markov's inequality goes as follows. This one, this is a general form, yeah. Okay. All right. So this is a general form, and of course, if your x is non-negative, if your x is non-negative, then the absolute value will not have any effect on it. So then you would have something simpler like this. Okay. All right. So, but this is a general form, right? Keep to the general form. Okay. Then from Markov's inequality implies Chebyshev's inequality. Okay, so you do a replacement. Simply do a replacement of x with centered, right? So generally, so this is mu. So you would have sorry. Bounded by the variance of x over alpha square. Replace and then choose k equals to 2, right? So the Chebyshev's inequality is a special case of your Markov's inequality. Now, this is the general form for your Chebyshev's inequality, right? So I think in some textbooks, right, you may have come across some formula like this. So let's say for this part, right, you take alpha equals to k sigma, right, where your variance of x is sigma squared, okay? So then you basically will get this result bounded by sigma square over k square sigma square, so 1 over k squared, right? Okay, so this is the Chebyshev result, Chebyshev inequality that you may have come across in some studies previously. All right, which basically says that the in layman's word, it says that the probability that random variable, realization, right, of a random variable escaping from mu by more than k standard deviation is bounded by 1 over k squared. Okay, so you can actually verbalize it, right? So let's look at some examples. Okay. Let me clear some things here. So some examples. So you take k equals to 1, right? So the chance that you escape from the mu, if you take a random set, that means basically, let's say you have some distribution. Doesn't have to be normal. It can be any distribution. So this is a distribution, right? So this is mu minus sigma. This is mu plus sigma, right? The chance that you get something like escaping, right? So if you fall somewhere within here, that is not, right? It's within sigma. But if you get something else, you are basically escaping from within sigma, right? It says that the chance of this happening will not be higher than, in this case, well, this is trivial, right? This bound is very loose, right? In this case, just say that it won't be more than 1. Of course, it won't be more than 1, right? So k is 1, k equals to 1 is trivial. So you can see that Chebyshev's bound is not very sharp, right? It's basically just a bound that is used. Later you will see that it's primarily useful for limit theorems, right? Which means if you take limit of n tending to infinity, that kind of situation. Otherwise, you want to use it as a bound for, like a bound for estimation. It's basically not very useful. So let's see, if you take k equals to 2, the chance that is more than 2 standard deviations, so this will be 2 standard deviations. That means escaping here, it says that cannot be more than 1/4, all right, and so on. Okay. So this is very what we call a very conservative bound. Okay. Right. So at least it tells you that well, if you find that somebody says that certain properties are certain values, but it violates Chebyshev's inequality, then it cannot be true. Yeah? So because the Chebyshev's inequality is very conservative. So if it violates it, then there's something wrong with the result that people give you, right? Okay. So these are the 2 inequalities, and then we have the next one. The next one is called Cantellis inequality. Okay, I think there are some members here who are in my buddy group, right? And we are working on some topic called the Stigler's law, law of eponymy. You basically can check whether these 3 inequalities are named after the person who found them or not, right? That will be an interesting check, right? Anyway, the law says that most of the theorems in mathematics are not named after the person who first discovered them, but they are rather usually named after the person who made them popular through writings or some other theoretical work. Not usually attributed to the discoverer. Usually the discoverer is buried in anonymity. Okay, this is somehow of a strange situation, but maybe not so strange because sometimes when you discover certain things, its value is not appreciated, right? Until somebody else comes along and say, oh wow, I can use it like this. But then since he's the person who shows that it can be used in certain ways, then people remember this person, right? Rather than a person who first discovered. So maybe that kind of phenomenon is quite common in real life. Okay, Cantellis inequality. So we have the following result. Okay, it's bounded by the following. How to show? This seems very curious, right? This seems to be a very curious result. So this sigma square is equal to the variance of x, right? Because your alpha is positive, your mu is expectation of x, right? Okay, to do so, we do the following, right? We use the so-called extended form of Markov's inequality. So the following. So the probability that so let me see. So first I simplify this. Yeah, let y equals to x minus mu. Yeah. Okay. So so this result this is equal to p. Okay. So here you see you are adding you add a constant on both sides, right? So it's okay, right? Yeah. And then you square this. Is also okay. Okay. So this is equivalent, yeah. Right? Because again you are applying the same operation, right? You square on both sides. Okay. And then over here you apply then at this step you apply Markov's inequality. So this will give you the bound, right? Expectation of this guy, right? Y plus beta squared. Okay, so this is one whole thing. And over alpha plus beta squared. So again, you treat this as an entire object, right? So basically, this is just a Markov's inequality. Okay. All right. Okay. So this is what we call an extended form of Markov's inequality, which basically is you do this 2 steps and then you get this. Now to continue, we know the following: the variance of y plus beta is equal to the following minus okay. So the expectation of y plus beta square is, so this one is basically, the left hand side is basically just variance of y, right? Because b is a constant, so it disappears. So it'd be sigma square plus this guy, right? This will be beta square, because this part is expectation of y is 0, yeah, because this is a centered form, yeah. Okay, it's a centered form. So your expectation of y plus beta is just basically 0 plus beta. All right. So you basically have this expectation is equal to sigma square plus beta square. So you get, so you come in here, so you get sigma square plus beta square over alpha plus beta square. Okay. So this is the so after doing, so I have this main part. So now I got this inequality. Now, once you have this inequality, note that because your beta is artificial, right? It's basically what we call a nuisance parameter. Okay. it is actually not something that you want to consider at the end, but it's useful as a kind of intermediate for intermediate work, right? So okay, you introduce a constant beta, which is positive, and you manage to get this inequality, right? The probability that y greater than or equals to alpha is bounded by this thing involving beta. Now, for it to be useful, you basically need to make sure that you have to choose your beta such that this bound, right, is as small as possible, right? Because we know that bounds, if this bound is very large, it's basically useless. For example, if you say that the probability of y greater than or equals to alpha is bounded by 2, that's basically a useless statement, right? Because we know that probability values, probability measures are bounded between 0 and 1 by definition, right? So if you get the bound being something that is large, right, is not desirable, right? So that means you have to find some kind of a combination of beta such that this bound, right, is as small as possible. Okay, so this is the idea now, right? How we can simplify. So the simplest way to do this in this case would be to use differential calculus, right? So you take the derivative of this bound with respect to beta, right? And you try to solve. Okay, so this is what we are going to do. So let me erase something. So you take the derivative with respect to beta. Right. So let's just do some calculus here. Times 2 beta plus times 2 alpha plus beta, right? And then over here is alpha plus beta squared, so get power of 4. So you want to force this to be 0. So you can see that basically the equation will be, so you factorize, yeah? So you basically factorize to alpha plus beta. Okay, and then you have, okay, basically this alpha plus beta. So the 2 is common, so come out like this. Okay, plus, oh sorry, I think this is a minus, right? It is a minus, yeah. So this is a minus alpha square plus, sorry, sigma square plus beta square. Okay, let's go to 0, right? So basically your alpha and beta are both positive, so you have to find it from here. Okay. So from here, so basically what do you have? So expand, you get alpha beta plus beta square equals to sigma square plus beta square, right? For it to be 0, so beta square disappears, and therefore you have beta is equal to sigma square over alpha. Okay, so this is the value that will minimize your bound here. Okay, minimize your bound. Of course, to be rigorous, you need to check the second order derivative, but that's a bit tedious, so we will skip that. Yeah, but if you want to, you can check it, and you can find that the second order derivative is positive at this particular value, right? So anyway, so you substitute this inside, so you will get the bound as sigma square plus sigma square over alpha square. It's so sigma power 4, yeah. Okay, because it's a beta square. So over alpha plus sigma square over alpha square, right? So this one, if you so for this, I leave it for you to complete. So it's just basically some simple algebra here. You simplify and you will get this result. Okay. So it's a nice result, yeah. Okay. For this part here, generally it doesn't really matter if you do it like this, because most of the time we are going to deal with x being continuous, yeah. So if x is continuous, then the equal sign here is not important, because at single points the measure is the probability measure is 0, right? Okay. All right. Okay. So this is Cantelli's inequality. So now we have learned three inequalities here. Then okay. So before we move on, is it okay for everyone, these inequalities?
Yes, doctor.
Okay. Let me just show some examples. All right. So you have, let's say, suppose your x, right, is your x is chi square, right? Chi square with 1 degree of freedom. Okay. Maybe, okay, let's say 10 degrees of freedom. So the chi-square of 10 degrees of freedom will look like this. It has a mean that is, the mean of the chi-square is equal to its degree of freedom, right? So around 10. Okay. So suppose you say you want to find the probability that, let's say x, right, exceeding 10. Right? Okay. So if you use Cantelli's, if you use Markov's inequality, it says that this is basically bounded by expectation of x. So here your x is non-negative, right? It's bounded by expectation of x over 10. So is it useful here? Here your expectation is still 10. So this is 10. So this is basically trivial, right? So this is trivial. Okay, so so this is not very useful. Let me see, if let's say you have 20. So let's say you have 20, right? That means over here. So basically this tail, right? It is saying that, okay, without calculating it, it says the probability of this will be bounded by, so it will be 20, right? Be bounded by 1 over 2. Okay, that means this this tail here, right, cannot be more than 50%. Okay, and so on, right, and so on. Okay. Now, if you try to use other, so this is based on Markov's inequality. Right. So how about Cantelli's? So Cantelli's inequality says the following. So P of x minus mu. Okay, just to recap, right? Alpha square. Okay. So here, your mu is already 20. So okay. So let me see. So mu is 10, right? So mu is 10. So you take alpha equals to 10. Then you will get 20. All right. So you take this to be 10. You take this to be 10. So you get 20, like here. So this may be bounded by the variance. Now, the variance of the chi-square is twice of its degree of freedom. So you got 2 times 10 over 2 times 10 plus 10 squared. Okay, so let's see what you get. So you get 20 here. So you get 20, 120. So this is 16. Right? Oh, you can compare these two bounds. Which is sharper? Which one is sharper? Sharp in this case means tight, right? That means it's close to the truth. Of course, this probability has a value, right? It's basically area under the curve, right? This is basically a bound, right? So if a bound is sharp, that means this bound is very close to, is closer to the truth. Which one should be closer? This one or this one? Which bound is sharper? The Cantelli or the Markov in this case?
Seems like it's Cantelli. It's Cantelli because it's a smaller value, right? This means it's sharper and closer.
Yeah, that's right. Usually the sharper one is the one that is smaller, because the bound that is smaller is basically more useful, right? Because you know that it won't, at most it goes to until this level, this particular level. So if this value is high, it's basically useless. Like you bound a probability with the probability is bounded by 2. It's basically a useless statement because I know that it's already bounded by 1, right? So you say it's bounded by 2. Of course, it is a true statement, right? You can even say it's bounded by 100, right? But it's basically a useless statement because not very helpful because is too the bound is too wide. So you're admitting too many possibilities. All right. Okay. Just for curiosity, so we may actually want to calculate what this probability is. So I'm going to just calculate it in R. Just a minute, yeah. So the actual value is from R is 0.029. So 1/6. Sorry, am I doing it correct? Let me see here. 0.029. Did I make some mistakes in calculations here? So this one is, the actual value is 0.029. Oh, it's correct lah. So 1/6 is what? 1/6 is half of 1/3, right? So 1/3 is 0.333 something, right? So half of it is 0.167. Correct lah. Okay. So of course this bound is better than this bound. This is 0.05. So sorry, this is 0.5. Okay. So this is put it on a line here. It is this is 0. So answer is here. So this bound is here, and 0.5 is here. Right? So this bound is definitely sharper, right? Okay. So this is an example. So let me look at another example. So let's say, suppose your x is normal. Standard normal, yeah, okay. So you cannot use the result of Markov's inequality that is positive, okay, but you definitely can do the following. So you could find this bound. Let's say you could have this. All right. So for example, if you want to make things a bit simple here, you could actually square this. This is one possibility. So basically you choose k equals to 2, right? If you choose that, basically, or of course, basically, then that will be basically just your Chebyshev's bound, right? It's okay, we can try that. So over here, I know that my expectation of x squared is basically 1, right? Because your mean is 0. So basically, this is variance x plus expectation of x squared, right? So this is 1, this is 0. So basically, you have 1, okay? So I know that this is bounded by 1 over alpha squared. So, but this one is basically the same as this, right? Yeah, because of symmetry, right? So you have this result. And basically these are the same thing, yeah, because since this is centered at 0, so you want it to be, so alpha is positive, yeah? So alpha here minus alpha here. So these two parts are symmetric, right? So basically you can say that this is twice of the tail, the right tail. And therefore you can have a bound that is like this. Okay? So yeah, so this kind of inequalities can help you get bounds for probabilities, and this can be useful when you do theoretical work, right? Because sometimes evaluating the value of a probability is unnecessary, and it may be very difficult to evaluate. And so therefore, an alternative is to work with bounds, right? And to work with bounds, you must know some of these inequality results. Okay. So let's say, let's check, right? If your alpha is 1.96, we know that P of x greater than 1.96 is what? Anybody? From normal distribution, 1.96 magic number. If this is 1.96, what is this tail amount? Anyone? $0.025. Okay, great. Suta. Okay. So this is close to 2, right? Close to 2. So you know the empirical rule, right? Plus minus 2 is about 95%, cover 95%. So this is one side only, so it's half of half of the remaining 5%. So that's 2.5%, right? So I know that it's 0.025. Let's say what the bound is, right? So the bound here is 1/2, 1.96 squared. This is about I'm just going to take this as 2. So this is roughly about 1/8, 0.125. Okay. So this so you get a bound like this. If you want to, you can compare it with the result that you get from Cantelli. We use Cantelli. Cantelli, then you basically have the following. Just Cantelli. Okay. So you have so Cantelli, let's say you have this. Right. So here your mu is 0 and your alpha is 1.96, right? So and your variance here is 1. So you basically have x greater than or equals to 1.96 bounded by 1/1 plus 1.96 squared. This is about 1/5. Okay. 1/5. So not so good, yeah. So for Cantelli's bound is actually not as sharp as your Markov's bound in this case. Okay, so all these bounds, it's not like one of them will always win, yeah. It depends on circumstances. Sometimes certain bounds are better in certain situations. All right, so this is just an illustration of what you can do with this these results, right, for certain distributions. Okay. Right. Okay. So I think let's take a break now. Take a 10-minute break now, and then we come back, right, with some additional results for inequalities. So I'm going to pause the recording now. Okay. So let's continue, everyone. All right. Okay, so here in this section, we're going to talk about a few things. First, we talk about something called a convex function. Right. Before we come to the inequalities, we talk about a kind of function called a convex function. So the opposite is the concave. This is the opposite, right? So what is meant by a convex function? So so we can say the following. Okay. So so let's say you have a function that's going like this. This is a function f. Okay. Now, if you have 2 points here, let's say this is x1, so this is your x, this is your fx. Okay. And you have another point here, so this is x2, right? Then you draw a you draw a secant line through these 2 points. Okay. So you have these 2 points, right? This is a secant line, right? And then you will see that this will be, so then you consider any point within this interval x1 and x2, and this point is constructed by as follows: p times x1 plus q times x2. So your p plus q is equal to 1. These are basically just a proportion. So if you take a weighted form of these 2 points, you will get some point that's in between. Yeah. All right. Okay. So now if you evaluate, so this is it. So let me see. This one is this is your function. So this is let's say your linear function here. This is y. Yeah. Okay. Now you can see the following. Y. So at this point, it is okay. So at this point, so this you make a projection from here to there. You basically have so this value here is basically f of p x1 plus q x2, right? This point, okay? You're basically evaluating it at this particular point, right? Whereas over here, so this part here is it will be something like this: p of f. So this is so this value here is your y of p x1 plus q x2, and it comes to here as the following. Okay. So you can basically build a linear equation since you know x1 and x2, and you know the slope, right? So the slope here you can tell, right? So the slope here, this will be basically fx2. This is the height. So over here, this is fx1. So the height here is fx2 minus fx1 over the base is x2 minus x1, right? Okay, so basically, you can construct an equation for this linear secant line. And then after you have the second line, if you plug in this value here, px1 plus qx2, you will get this result, right? So I will skip those details later, which you can follow later in the notes, yeah, right? So basically, it's nothing much. It's basically you have a linear equation here. You substitute px1 plus qx2, you will get this particular value, right? And this is the value evaluated at the curve f, okay? So very clearly from geometrical consideration, right, you will see that your f of px1 plus qx2 is lower than or equals to, so this value is bounded by this value, right? P of x fx1 plus q of fx2. Okay. All right. So this is an equality for convex function. So if your function is convex, it means if you draw a secant line on it, this this particular value here, yeah, will bound this particular value. Okay. So you have an inequality like this. So this inequality occurs for convex functions, right? If you have concave functions basically you flip, right? So basically you have a function that goes like this, concave, something like this. Okay, this looks like the entrance. How to remember convex and concave? Roughly you can see concave, right? See the word cave here. So this, if a function looks like this looks like the entrance of a cave. All right. So otherwise you always get confused with convex and concave. So the convex is basically the opposite of concave. That's it. So you have, again, you draw a secant line, right? So draw a secant line, you have these two values. Okay. So again, you have px1 plus qx2. Okay, so you make a projection here, and you also have a projection here. All right. Let me see. Just a minute. So okay. So basically over here you will have p of fx1 plus q of fx2, and this will be f of px1 plus qx2. So again, in this case, they will dominate, right? Your function here will dominate, right? So f of px1 plus qx2 will dominate this thing. Okay. So basically, it's very simple. Convex, the function of some weighted average is bounded by this weighted average of the function. And when it's concave, you just reverse the sign, right? So you just need to remember one of them, and the other is just you flip the inequality. Okay. So this inequality is obtained from geometry. It's a purely geometrical inequality. Okay, in case you wonder how a lot of these inequalities come about, they basically refer to some facts in geometry. Okay, so if you, that's why I encourage you to always think of things geometrically, because that would help you solve a large class of such problems, yeah, that are based on geometry. Okay, so we have this result. And now we are ready to talk about something called the Jensen's inequality. Let me just clear some space here. So now we can talk about Jensen's inequality. Okay, now Jensen's inequality states the following. the function of an expectation of x is bounded by the expectation of the function of x. Okay? If you look at this form, right? So this is basically, so this is your function, right? This expectation of x, basically you are giving a weight, right? For each of the possible values of x, right? You're putting a weight. So this PQ here plays the role of the weight. In fact, this one can be extended to multi-dimensional. That means you have P1 x1 plus P2 x2 plus until Pn xn, right? It will be true, but of course then you won't have this geometrical object, right? That you can sketch here. But it is is analogous, right? So this part here plays the role of your expectation, and this part here you see these are the weights, right? Okay, so again, so these are the evaluations f of x. So it becomes the expectation of f of x. Okay, so Jensen's inequality shows this if f is convex. Okay, so if f is convex, you have this result, Jensen's inequality. So now let's look at some examples. So let me just write it again. Okay, the function of expectation of x is bounded by the expectation of the function of x. Sorry. F is convex. Okay, let's think of some convex functions. Let's think of some convex functions. Anyone? Let's think of some. The convex function should generally behave like this, right? So that you put any function where you put a secant line. So this part here, right, for any 2 points within. So this value is bounded by. So this value dominates this value. So you will have convexity. So any ideas? Simple ideas. Give a simple idea of a convex function that you can think of.
X squared.
X squared. Okay. So x squared goes like this, right? So we put a secant line like this. So definitely, so let's say secant line like this. So definitely any point within is dominated by the point on the line, right? So yes, x squared, which means you have, if f is x squared, then expectation of x. So this is the argument, right? So square, all right, will be bounded by the expectation of x squared, which means yeah, so basically, which means the square of the mean is bounded by the second moment. Okay, this is an interesting result. And of course, why is it so? Actually, this, right, is actually you can rearrange it, right? So basically, you rearrange it, you get the following. And what is this? Anyone can recognize this?
Is variance.
Yeah, variance of x, which is basically trivial. This is a trivial result, right? Because the variance of x is, okay, is your variance of x is non-negative quantity. So basically, if you apply Jensen's inequality with the quadratic function, you basically recover the trivial result, the trivial relationship, which is the variance of x must be non-negative. Okay. So that is nice, but it leads to something that is already trivial. So can we look at other examples of convex functions? Don't have to go far, just use the common ones that you come across. Anyone?
If it's x squared plus 1,
X squared plus 1, it is still, yeah, it will be still convex. You will also get some inequality. So then you will get this result. X squared plus 1, is it?
Yep.
X is x squared plus 1. So then you will have let me see, this one plus 1, expectation of x squared plus 1, which you can see that it leads back to the same thing because your constant cancels. Okay, so adding a constant will lead to the same inequality. What other function that you use all the time? Very common. Exponential of x. Okay, that's great. Exponential of x, so how does it look like? Exponential of x is going like this. So definitely convex, right? Because it's going up like this. So you pick any 2 points, put a secant line. So definitely any point within is on the secant line and dominating. Okay. So your e of x, fx, e of x is convex. So if it's convex, then you can apply this inequality. So let's see what we get. So expectation of, so exponentiation of, so replace x with e of x, expectation of e x. Okay, which basically means e of mu is bounded by expectation of e power x, which means you can further get some results, mu less than log of e of ex. Right. So you know that, well, it depends on what you want, right? So if you are interested to find out the expectation of this random variable, you know that is the lower bound is e power of mu. Okay. And depending on what you want to do, sometimes this form is okay already enough, or sometimes you might want to look at the log form or whatever. So just to let you know. So this is very interesting here. You notice that if you put a t here, you will get something like this. So I mean, you basically take e of tx, right? So basically you will have this, and what is this form? Anybody recognizes this? Expectation of e to the power of tx. What is it?
Moment generating function.
Yeah, correct. So this is the moment generating function. So the moment generating function is bounded, it has a lower bound given by e of t mu, where mu is the mean. And this one, so you can further find if there are inequalities related to exponential function, you can further connect, right? So yeah. So sometimes when you see inequalities that involve these kind of things, the first thing is to start thinking about that they are probably obtained using this kind of Jensen's inequality with certain convex functions. Okay. So here are two examples. Of course, we know that if the function is concave, right, this will flip for concave. Okay. So give me some examples of a concave function. You can also get inequalities, but in the sign is reverse. Minus of x squared minus of x squared like this. So flip down, okay? Okay, this is concave. So if you do it like this, I think you will get something back like this result. You know why? Okay, then you will get minus of expectation of x squared greater than or equals to expectation of minus of x squared. Okay. You know, you have minus sign here, so you multiply both sides with negative, so the negative will cancel, and this sign will reverse because you multiply by negative. So you basically get back the original result here. So that just by introducing a sign to it, basically will lead to the same inequality that you get without the sign. So maybe we try some other functional forms. Yeah. You got something like this, right? What is some other function that is closely related to the exponential function?
Log x.
Ah, okay, log. It's nemesis, right? Because when the log meets the exponent, they kind of like kill each other, right? Because it's the inverse function. Okay, so you have this. Take fx equals to log of x, right? So then you will have, so okay, if you sketch log x is like this. Okay, so it keeps on going like this. So this is 1, so this is 0, right? So basically when you put a secant line through it, you see that at any point, right? Any point in between the point on the curve is dominating the point on the straight line. Okay, so the result will flip. Okay, it's very simple. So any function that you want to consider, just do a sketch. That's where your calculus skills calculus skills come into the picture. If your calculus is a bit rusty, it is a bit you need some practice to like graph sketching and things like that. Because otherwise, it's very hard for you to determine whether a function is concave or convex. So now you know this is concave. So know that the log of e of x, okay, will be larger than or equals to the expectation of log of x. Okay. So in this case, in fact, I get an interesting result, which is the expectation of the random variable log of x is bounded by the log of mu, where mu is the expectation of x. All right, interesting, right? Because so just by applying this inequality, you get a bound for some random variable. And this random variable this expectation may be very hard to calculate depending on what is your x, what is the distribution of x. And in fact, by just applying the inequality, you already have an idea about its bound. Like it cannot exceed certain value, right? So this is useful information as well. Okay, so let's take one more example before we move on. One more example for a concave function. A very simple one. You have been seeing this function appearing quite often just now in the Markov Chebyshev inequalities. What function is that? Anyone? What function did you see just now in the Markov and Chebyshev inequality? Normal. Normal. The normal distribution uses the exponential function. So the normal, normal distribution is just a name for a function that uses exponential function. So we already covered exponential function just now. Of course, e of minus x, right, is decaying like this, right? So what is this? Is it concave or convex? Concave or convex? Yeah, it's convex, right? Okay, because at any point between the value evaluated at the straight line is dominating the value on the curve, right? So yeah, this one is convex. So of course you can derive. I leave it to you. Okay. So again, yeah, Sutta said something like this. So this is also okay. Interesting. This one. This one. So this is also convex, right? Okay. You look at a concave function. Very simple one just now. In the inequalities, what do you see coming out very often? So Markov's inequality. What function do you see here?
X power to 3.
X to the power of 3. Well, I think it's something like this, right? Sorry, wait. X to the power of 3, if you have between 0 and 1, it will become very small. Right, become very small. And then after that, it will start to shoot very quickly. Okay. So you put any 2 points. The thing with this x power 3 is that it's not so simple. The convexity it's the convexity and is only defined over certain intervals. All right, like for example, over here you'll find that part of it is I think this part here is actually concave, but this part here is convex. So not so simple. All right, is convex for x greater than 0 and concave for x negative. So maybe a bit hard to use this inequality. Yeah, because it will depend on the particular intervals of x that you take. Just do something simple. What is common here? What function is common here? It's very obvious. And sometimes the most obvious thing is the hardest to spot, right? Because it seems like it's not special enough for you. Then you don't spot it. You got some very weird functions like sine, hyperbolic function, those attract your attention. But here you see, you kind of like miss it. Can anybody see it, the function? It's a very humble function. Humble people are missed all the time, right? People go for the flashy type. Anyone? Yeah, that's right. Aishwarya. Absolute function. Absolute of x. So absolute of x is actually, wait, this is oh, this is actually concave. Sorry, this is actually convex. All right, sorry, I messed up. All right, so yeah, okay. I wanted to say something about the absolute function, but this is actually convex, right? Because you put any 2 points, the line is dominating, right? So it's actually convex. Okay, never mind. So this is actually convex, right? Okay. Square root of 2, square root of x. Okay, interesting. Square root of x, you will have like this, right? Okay, square root of x. And it's definitely concave, all right? So that's good. Because if your x square is convex, right? So it's inverse. So in this case, you have, let's say, for positive, right? For positive values, you can invert it, and the square root of x will be only for positive x, will be concave, right? Okay, because any 2 points, your value on the curve is dominating the value on the line. Okay. All right. Okay. So good. So for that, we will have, for example, we will have a square root of expectation of x will be larger than or equals to the expectation of square root of x. Okay, which gives you expectation of x is greater than the square of the expectation. All right. Okay, so you get some inequality like this. Okay, so I think that's all I want to talk about for Jensen's inequality. All right, we have looked at quite a few examples. Yeah. Okay, then we move on to a result called Holder's inequality. So Holder's inequality says the following: if 1p plus 1q is equal to 1, and then the absolute of x times y is bounded by this result. So we're not going to look at the proof a bit involved. We're just going to learn how to use it, all right? Okay, so of course your expectation of absolute x must be finite, expectation of y must be finite, all right? Otherwise this will not hold. So yeah, so if you have, if 1 over p plus 1 over q is equal to 1, this is a constraint, then it says that you have this result, all right? So this is like, so you can get all kinds of results, like for example, the p is equal to, so 1 over p plus 1 over q must be equal to 1. So if your p is 2, then you can take q equals to 2, right? Okay, so this is a special case, right? When your p is equal to q equals to 2, then you have expectation of absolute xy is bounded by expectation of x squared. Because if you have 2, then absolute, you can remove the absolute sign, right? Because the square. Then this is 1 over 2, so the square root, all right? So basically, yeah, so this is what we call Schwartz inequality. Okay, now Schwartz equality is a very interesting result. Suppose you replace x with the centered form, x minus mu x. Then y with y minus mu y, right? Let's look at what you will get. So you get expectation of x minus mu x, y minus mu y, bounded by square root of expectation of x minus mu square to this, right? All right, okay. So this is basically your variance of x, and this is your variance of y. Okay, so basically you have the following result, right? The expectation of this thing, right, is so this is yeah, you have your expectation of this thing is bounded by the square root of the product of your two variances. In fact, this part here is your let me see. This will be this is something like your covariance. Except that it's got an absolute sign here. So this is something like a covariance like random variable. Okay. So you know that you have some result like the covariance of x, y divided by the square root of the variance of x times variance of y. This is your correlation, right? Between x and y. Okay, so this Schwartz inequality gives you some related results. Okay, when you make substitution. Okay, so the special case is Schwartz inequality. Of course, for other cases, you can try out, like for example, if you take p is equal to 3, then your 1 over q must be equal to 2 over 3, and therefore q must be 3 over 2. So then this would give you some result like this. It will be a bit complicated. There will be absolute power of 3, that's the square root. Then e of absolute y, 3 over 2. And you have 2 over 3. Okay. Yeah, so for your level, I think most of the time, you will be just concerned with the special case of Holder's inequality, right? Because the other situations with different values of P and Q, when your P goes to 3 and all that, then your Q starts to get complicated, and they may be useful for some more advanced work, but generally at this level, you don't need to use them, right? So you just restrict yourself to Schwartz inequality. Okay. Now let's see what kind of results we can get from Schwartz inequality. So this from here, okay, maybe I just erase, clear the board. So I have Schwartz inequality. Expectation of absolute xy is bounded by square root of expectation of x squared, expectation of y squared, okay? Okay, so suppose if y is equal to let's say log of x. Then I would have expectation of absolute x, log x, bounded by okay. So basically you can just plug in, right? All right, some other examples, like let's say if your y is 1 over 1 plus x squared, then your expectation of absolute x over 1 plus x squared will be bounded by expectation of 1 over 1 plus x. Okay, maybe I just make it simple without the square. Okay, so with this Schwarz inequality, you can basically, so it gives you another way to find expectations of bounds for expectations of random variables. Okay, so suppose we have some, let's look at something that's more concrete, right? Let's see. So suppose your x takes a certain, if your x takes a particular kind of distribution, right? So let's look at what would happen. So for example, over here, you can also do something like this. If you take y equals to log x over x, then you would get expectation of, you replace, you will get absolute log y, because this, when it multiplies with x, it will cancel, but then you will get bounded by expectation of x squared times this. Okay, so you can also you can also pick things like this where sometimes the x can cancel with the x here. All right. So you can get some. So this is basically simpler. And once this becomes simpler, this part will become more complicated, right? So it may or may not be useful depending on how easy is it to evaluate this kind of functions. Okay. All right. Okay. So I think so. These are all the things that I want to talk about for inequalities. All right. So in the tutorials, you will have more chance to practice on using these inequalities, right? To get some useful results. Okay. So tutorial 5 has been posted. So do take a look, and this on this Thursday we will. So we will assign, ask the students to look at some questions, right? So you can try it this week already, and we will discuss it next week. All right, okay. So that's all for today's lesson, all right? Is there anything else you want to ask? Okay. Okay. If not, maybe later when you have, when you work out the problems and you come across some questions, then you can ask later. All right. Okay. So that's all for today. Thanks for listening.